So now he is highly accomplished with over 400 peer-reviewed journal articles and 47, oh my gosh, U.S. patents awarded already. So Quanxi now is Los Alamos Foundry. So it's probably the highest technical ranking in Los Alamos. And then how many do you have? You said a few, right? And then he's also the director for the Center of for Integrated Nanotechnology at DOE Nanoscale Science Research Center, operated jointly by Sandia and Los Alamos. Quanxi won many different awards and honors, and then I will not read them, but just want to highlight he's also a fellow of American Physical Society, Material Research Society, American Ceramic Society, and the American Association for Advancement of Science. So with that, let's welcome Quanxi. About the same piece of titles, you can read it.
Okay, can you hear me? Okay, good. That's good. First, thank you so much, Billy, and also thank you so much. So this one, sound, right?
I think so, yeah.
Okay, good. And also, thank you so much, Professor John Rustin, for the invitation. So wonderful campus. I really love this place. I found this wonderful. It's the first time into this campus. It's really wonderful. Okay, so I think probably I will go ahead to start to give my talk. Actually, Judy, you are very, very kind and for the introduction. So what I'm going to do is I'm going to discuss this, but before I do this, I'd like to say something. Since Judy mentioned, I'm the director for this really a nanoscale scientific research center. I'd like to really say something about this. Okay, so DOE is about 10 years ago really set up this nanoscale science research center. And if you look at the map, here we have the Brookhaven, you have Argonne National Lab, and then you have Oak Ridge, and then you have Lawrence Berkeley. In New Mexico, we have this CENT, the Center for Integrated Nanotechnologies. It's one center, but jointly operated by Sandia and the Los Alamos National Lab. Actually, there's two facilities. One over here we call, what's going on? Sorry about this. Something is not right. Hopefully this will. So here, we have this jointly operated by Sandia and the Los Alamos National Lab. And actually we have two facilities. Here we call the core facility, and then over here we call the gateway facility. But if you quickly look at this, like over here, you look at the size and also operation. So we have anywhere, depends on what time you ask. We have probably 50 to 60 scientists plus technologists. And also we have right now this year we have almost 500 users. Keep this in mind, since this is a user facility, it's really. Since here we have a lot of faculties and also postdocs, students, keep this in mind. This is free, really, that's free, nothing. So you can really access, later I will show this, all the facilities, the capabilities, you don't pay anything, okay? So you can just write a user proposal. If the user proposal is granted, that's a peer review process, 2 pages, very simple. And you can use really the facility for free, okay? But of course, you have to pay your travel, your meal yourself, but otherwise, the facility-wise is for free. But if you do, see something like industry, very often they do something, they only do that for themselves. In that case, the DOE's policy is full cost recovery, okay? keep that in mind. And also, like see, later I will mention about this, how we do this. We have many postdoc students, just join us over there. And here just see what I'm talking about for the user facility. It's very, very different from the, the very conventional user facility. People probably know about like a singletron, neutron facilities. You have a big monster, this kind of things over there. But here we are talking about the user facility. It's really defined by a scientific field, not specifically it's really implementation. Okay? And also, see, the scientists over there support the user, our users. So not only the equipment, we also have the scientists over there. They support you. Later I will show you examples. And also the capability, like I mentioned, involve hardware and also plus the research expertise. Okay? Keep that in mind. If you look at this, it's very often we have the user really come to us, so they propose something. And in the sense, especially we're talking about the nanomaterial integration. Los Alamos is very, very strong for material science. And Sandia, that's very, very strong for the engineering side. They make electronic devices, right? So actually, when you marry these two together, this is some really very, very unique capability later I will show you, okay? And then, of course, we have this, talking about the more like making. You synthesize the material. You can also think about characterization. I will show you that as well. And then that's really understanding, do the theoretical part. So basically, you fundamentally understand what's going on there. So why we are talking about the integration? Okay, that's probably, you will ask this question. You think about this, all the nanomaterials, if you just work on nanoparticle or a single carbon nanotube, what you can do with it? Almost nothing, right? It's probably you will learn something physics, but really the impact over there, it's almost, you cannot do too much. But really the things you are talking about, how you can integrate this nanomaterial together, you get the functionality you want. Think about, how the transistor, right now, the very large scale integrated circuit work out. At the beginning, you have the diode, resistor, capacitor, transistor, everything together. But later, the way today, look at our cell phone, everything, that's really the integrated circuit. Think about that, right? So that's a way you make the difference. Similarly, if you think about the nanostructure material, you can have like a quantum dots, nanowire, everything like that. If you really want to have the impact, you have to make them into the system. That's really the things we are talking about, the integration. Okay? Here quickly, just probably show you two more slides. We have 4 thrusts, the way we structure our center. We have the nanophotonics, optical nanomaterials. That's a lot of, we do the like metamaterials, all this kind of capability. If you go to the website, you will see that. And then we have this nanoscale electronics and mechanics. Okay, that's, just look at the title, you know what we are talking about. And then we have this soft bio, and then we have a theory. The way we structure this center scientifically is the 4 thrusts. We structure this. Okay. Oh, what's going on here?
Our computer.
Oh, that's your computer? That's my computer.
Oh, you're using yours? Then the Los Alamos. Ours is better.
So this is something I just quickly show you some, special strengths from, this center. Here, just for example, this ultra-fast spectroscopy metamaterials we do, and like a nanomanipulation, nanomechanics, and also nanofabrication integration, I mentioned earlier. Another thing is really the discovery platform as well. So actually, we do this a lot. Like say, if you want to have something that's a standard, like a microchip, we have this cantilevers, like this, this kind of microstructure. If you want to put your device or something over there to the measurement, we can provide you this kind of chips for free as well. Okay, we can just mail this to you. Okay, if you write your proposal, okay? So how things work out? Here, I just show you one, this is the last slide, before I go to my technical talk. Let's say, for example, this is our user from, from university. The proposal is really this, here, the title. The way you see, for example, like a scent, our scientists, we know how to synthesize the material. We synthesize material for the user. And then we have the nanofabrication. We fabricate the device for our user. And then we even do the characterization for our user. And then finally, you publish. Okay, that's really the DOE they want. This is from basic energy science. The way they judge us, how successful we are, is publications. Okay? So that's the way, you see, we form this circle. We do science. We do collaboration together.
It's in Nature. I hear a lot of those papers are fake.
Yeah. We discussed about this. Oh, what's going on here? I will eject this. What happened? They don't let me do it. Okay. Okay, that's something more like a commercial. Sorry about that. Here I just started my technical talk, but you can see over here, and there's a lot of people getting involved. And just about 2 years ago, I moved from technical side to manager side. So actually, a lot of things, I'm not, so someone else did it. Okay. So here's a quick outline. What I'm going to do, I will give you, just make sure we're on the same page. I will just give you a quick introduction, and then we'll give you two material systems, so how the effect of interfaces on the property of the material, and finally just give you a quick summary. Okay. So since we have a lot of students over here, what I like to do is just quickly show you why thin films. Okay. Probably everyone know. So typically, if I put the material just based on this cartoon drawing, you take a look at, you have single crystal material, you have polycrystalline bulk material, you have thin films. Okay? But for the bulk, the single crystal, mostly we as a physicist, we study the intrinsic physics. It's so clean, such a nice system. But at the same time, the challenge for this material is really the manipulation, how you can really manipulate the structure. Oh, I hate this. What's going on here? Maybe is.
Should you turn off your browser? Or
No, I think it's a conflict between his thing and the projector is probably trying to access the screen.
So which one?
Pick.
Well, I think he doesn't use his
You think that's a.
clicker, then it'll probably not, but I don't know.
So I remove the remote control, see what happened. Okay. But over here, when you're talking about the, here, for example, and also a lot of material, the single crystal material, you cannot have a, large size. But of course, some other material like silicon, you have 12-inch wafers, but a lot of material you don't, right? Another sense, a lot of material you even cannot make a single crystal. Just give you one example, like a uranium oxide. U02, you get a single crystal. U308, you don't. Okay? No one has ever grown this kind of single crystal material. Someone probably here probably they will say, no, probably. If you know something about that, let me know. So actually, a lot of material you cannot grow that. Okay? But when you go to the polycrystalline material like over here, of course, it's an easy process. You can press them, you make a nice, a bulk chunk of material. But at the same time, look at this just cartoon, the green boundary issues, a lot of other issues over there. Okay? Of course, when you study the electronic properties, the green boundaries always, affect your fundamental properties. Of course, you do thin film actually give you a lot of this kind of a good way you control it. One thing, of course, you can think about the artificial architecture, like see over here. For example, superlattice. A lot of people are working on like this topic, even in our university over here. All this kind of things, like say you have two phases of material, you make this kind of pillar structure, right? So I will show you some example like that. And also you can control the dimensionality. Another thing is really, since this is a thin film, you can really grow the material at far from or near equilibrium, that kind of conditions. With all that, actually you can do a lot of interesting things you cannot do over here or over here, right? But at the same time, I just want to make sure you understand this. So also, it's a very, very complex process. Quickly, for students' purpose, well, what's really the advantage of the epitaxy? But here, you have this substrate, and then you have the thin film. It's not in scale, of course. And due to the lattice mismatch, so you can really grow the material. If that's relaxed, you form the defect. If not, the strain. So basically, that's really the way you look at the very, very simple things. You look at the lattice parameter, like a film, the substrate, and then look at this mismatch, and then you can think about is really epitaxy or not, okay? You can do it or not. When you do this, there's many things you can think about. For example, if the single crystal is not available, of course, this is not a single crystal material, but they are very close. I will call them quasi-like, right? But also another thing is you do multi-layer, since you can always use the bottom layer as more like a template. That's an induced preferential orientation. You can think about it that way. Another thing, let's say over here, you can do the strain annealing. You can also lock into the crystal structure so that you can control the phases, right? So if you do like that, it's more like a pressure effect. And then, of course, you can also do the interface engineering, for example. And then you can do the chemical or electronic doping. That means like you have a complex material, you can artificially, you stop. For example, strontium titanate. You can stop at the strontium oxide, you can stop the titanium oxide. And then you can build things on top, right? You can do all this kind of fancy stuff. The single crystal is very, very tough. It's a challenge to do, okay? To me, that's more like if you can really control everything, that's really your design. You can do everything yourself, okay? Here, just quickly, one more slide. The intro part is really homo-heteroepitaxy. For the people, like say the students not in the material field, you think about this. Typically, think about this apple and orange. So depends on how you do it. You can think about this. If that's a different material, we call hetero. If that's a same thing, that's homo, right? So, but again, depends on how we do it. Say, for example, if the lattice mismatch is very, very small, very often you can get this quite a nice epitaxial growth. But if, the lattice mismatch is big, then you introduce the interface, the mismatch dislocation, okay? That's just something, keep this in mind, okay? So that's, just to give people some background, and then in this way, we will on the same page when I discuss the experimental results, okay? Here just to show you this different approach to tune the functionalities, like see in this epitaxial, this material. So one way you do is you can put, like see, this substrate is the same film, it's epitaxy. You can put the particles inside, okay? Or another way you can do it, we call laminar-like, this is a superlattice structure. You can do the layer by layer. Or you can do this pillar, okay? So I will just show you a couple examples quickly. See, how we can really use this kind of architecture. You can tune the functionality that you want, okay? Let me give you first one. It's really nanoparticles. That's about, more than 10 years ago. So actually, we developed this. We dope like a YBCO with barium zirconate. Okay? You see, oh, here's a TEM. You look at the nanoparticles, the barium zirconate, in this YBCO matrix. Okay? But the interesting thing is when you introduce nanoparticles, you think about this. This one is an insulating phase, but the superconductor is YBCO. Well, sometimes you can think about it, you say, well, that's a defect in your material. This defect typically we say it's bad, right? But actually when you do this, you can enhance the flux pinning properties. the superconductor field, people call that. For example, this one, the open circle, that's a current density versus magnetic field. Without a nanoparticle, you see, especially at a high field, the current drops a lot. But with nanoparticles, keep this in mind, this is log scale. You really enhance the magnetic, the current capability a lot. Actually, currently, this pattern is licensed by the industry. That's almost like a standard technology. People right now are working on the coated conductors. Okay, this is a very, very powerful technique if you can control that. Okay, keep this in mind. If you can control, you can really, that's your design. Another one, superlattices. Look at this one. Like a strontium titanate, the barium titanate, this is a superlattice structure. This actually is from Darussalam, probably from Cornell University. So that's not our work. I just give you some introduction over here. So the strontium titanate is not ferroelectric. Okay, it's ferroelectric material. But the barium titanate, yes. When they do face these two together, like a superlattice structure, due to the strain effect, actually you can change this one like strontium titanate due to the tetragonality distortion. You can change strontium titanate to ferroelectric, even above room temperature. Okay, it's really you totally change the functionality of the material, the intrinsic property of the material. You can do. Another example, actually, people do superlattice. Let's say, oh, here, lanthanum aluminide, strontium titanate. Both this material, they are insulating material. But actually, when you face these two together, depends on how you terminate the interface, like over here or over here. Actually, you can change this to superconductor. Depends on how you do it. That's really just across the interface. You form this 2D electron gas. Okay, again, there's a several group from Stanford, from others, depends on how you do it. You see still insulating or superconductor, so many things you can do over there. You can really manipulate by controlling the interface, you can really control the functionality. Okay. Then one more example, that's from others, then I will show our work, is you do this pillar structure. Like a barium titanate, cobalt ferrite. The barium titanate, this is ferroelectric. You have this electrorestrictive effect. Cobalt ferrite is a ferromagnetic material. When you couple these two together, this is just the top of view. You look at this, the pillar, you have this kind of structure. You form this, nanocomposite material. Actually, you form this kind of new property that's electromagnetic or magnetic electronic property, the ME effect. So actually, from either of this, they don't. Okay, you really form some kind of functionality you don't get out from a single phase. Okay, so at Los Alamos, actually, we do quite a lot. It's not exactly really along that field. So basically, what we are trying to do is really how we can use this for example, it's more like material design, how we can use this controlled synthesis, and then we use advanced characterization, and with the theory computation, then we can predict, or we can really design some material system with controlled or desired functionality we can do. Okay, that's really something I'd like to show you some examples how we do this kind of business at Los Alamos, and also at Sandia, so we do this. But I showed this already. It's also about 10 years ago we did this. Like say when we put this two phases material together, and you can really depend on how you control this. You can do a lot of things over here. Again, that depends on how you grow the material. Like see, you can control the pillar width or feature size, and also if you think about this, you have an interface like this over here. You have the interface over here. So actually, you can independently control the lateral interface and also control the vertical interface. I will show you about this. Of course, when you do this, you have to think about how you design the material, how you can form this kind of spontaneous ordering, and the strain control, and also make sure that since you have two phases of material, make sure they don't mix each other, or you form like a reaction product that's a third phase. Make sure you will not do that. Another thing, the beauty, if you think about this one, is if you do single phase material, when you grow like a one layer material on a substrate, due to the lattice mismatch between the substrate and the film I mentioned earlier, typically you have a critical film thickness. Beyond the critical film thickness, the energy build up across the interface is so high, they have to relax. You form the misfield dislocation just right across the substrate and then film. However, when you do this, you can think about it, it's a vertical interface. If you have two phases of material, one material control another. Since basically each phase is more like a nano, that kind of dimension, right? So it also depends on how you control this, the thickness. You can control the strain over here, you can strain over here. Actually, you can really totally, it's not like the single layer material, since you squeeze it this way, you expand it this way, or, I said something wrong, maybe you squeeze this way, yes, you expand this way, or you expand this way, then you compress this way, right? But over here, actually, you can independently control this. This is really X, Y, Z. You can control them independently. Depends on the thickness over here. So I will show you that. If you think about this, a lot of things, the physical properties or the transport properties, they are related to the crystal, like the distortion. You can really manipulate the functionality over here as well. Here, just quickly, since actually Judy also has this setup, like the PLD things, for example, you do the pulse laser deposition. So basically, you do is really you can really do the layer by layer growth. I will show you this. So this just quickly just show the experimental tool we are using for, at least for this talk. And here just show you one example, okay? For example, let's see, just a cartoon, look at this. The single phase film, if you got a bismuth ferrite here, and this is strontium tandem. If you look at the crystal lattice parameter, if you look at this, the thin film, that's what you expect, okay? So basically, in the plane, you have a compressive strain, and then outer plane, you just expand it. For the metal oxide, it's another phase. If you put on strontium tannate, you think about the 45-degree rotation, and that's what you expect, okay? Actually, that's exactly, if you do single phase film, that's just what you say, okay? That's just a pure film case. Okay, that's exactly for these two phases you will see this. Okay, that's just experimentally you will see that. However, when you do this pillar structure, you see you totally switch this. Okay. Why is that? Well, that's really the vertical interface control your strain, not the lateral interface anymore. Okay, just to show you that. So actually, that's a very, very powerful way you can really control the functionality of it, or the crystal structure to that functionality. Another thing I mentioned earlier, you can go to very, very thick film. So typically, the critical film thickness depends on the lattice mismatch. It's anywhere from probably tens of nanometer, probably a couple hundred nanometer, that kind of range. Really depends on the materials we are talking about. But here we are talking about even you go to 1 micron, still straight. If you look at the lattice parameter, there's some, look at the bulk. For example, this is a barium tannate. Below this temperature, there's a tetragonal. Above this Curie temperature, the cubic. Okay, so the C does not equal to A. Okay, that's for the single crystal. But when you do this, the pillar structure here, for example, this top view, look at this. You have all this pillar inside, and then look at the vertical structure. And actually, you even go to 700 degrees C, you still have that kind of tetragonality. Okay? Of course, we cannot say whether it's ferroelectric at that temperature, but actually we check to 300 degrees C, still ferroelectric. Okay, you just really change the functionality you can do with it. Okay. Give you another example. Let's see. Here, just to show you the cross-sectional TEM. Let's see, for example, you can do this ferromagnetic ASMO material interface with MgO. We use MgO as a more like a control phase, or I call passive phase. RSMO as active phase. You can use MgO to tune the magnetic property of the RSMO. Okay? Same thing over here, for example, like a zinc oxide, RSMO. The zinc oxide is also the second phase. Look at this is cross-sectional, all this cross-sectional. And you see, it's a very, very sharp interface. You can really grow very, very high quality material. And then you can use this phase to control the RSMO property as well. And also, actually, vice versa. We haven't published that yet. Actually, since this is magnetic material, you have this magnetostrictive effect. When you apply a magnetic field, actually you can tune this property of the zinc oxide. The reason, since they are attached together, the couple, they will change the band gap of zinc oxide. Actually, you can tune the optical property of the zinc oxide. Okay, you can do like that way as well. Okay. Another thing, give you some other example. You can also do, depends on how much you put over there. Like say over here, you have the volume ratio. You put more, or you switch, right? Depends on A and B. So which one is the majority? You can do that as well. When you do that, for example, here is barium strontium titanate. Look at this single phase material. And we go to like 300 nanometer or 600 nanometer. We look at the tetragonality. As you see over here, when you put more, this is metal oxide. You see, depending on ratio, you can really change the tetragonality. Basically, you keep this material as ferroelectric. Okay. Since typically for this material, the Curie temperature is room temperature. That's for a lot of microwave device application. But here, if we want to go to higher temperature, for example, like a motor, automobile application or something like that, you want to higher Curie temperature. That's why we do this kind of stuff. I think I will skip this one quickly. Just show you something that you can do is depends on the ratio. Actually, for example, this one is RSMO peak. The MgO peak is over here. And if you look at the X-ray diffraction, you see, depends on the ratio, you can systematically shift the peak. You shift the lattice parameter. That's really the string effect. Okay? That's a several parameter you can do. Like so you control the volume ratio. You control also actually you can use a substrate. You can also change the material. Here I just show you MgO. Actually, when you do zinc oxide or ceramic oxide, they will give you different, basically give you different results. Okay.
So by how much you can change the lattice constant, like quantitatively?
It's about a couple percent.
So 1 or 2%?
Yes. So currently, I think that system is about 1.5% or something. Yeah. Okay. Another thing is really for this is recently we just did this. We found people probably over here, I don't know if you're working on this resistive memories effect or not, but something interesting you can do as well. You think about this, the oxide, the metal oxide, you do this resistive switching. Typically, that's the way you have two-terminal device. You can do like this. The way the understanding is that you form this filament. When you apply an electric field, you form the filament, and then you have this resistive switching properties. Or people do superlattice. You do this, you have to put a contact like this. They study the interface. But what you can do with this pillar structure, actually, it's more accessible, I call. So that's actually, you can get some very, very interesting phenomena across the interface. Over here, just show you the way the vertical interface, how they match together, and the TM cross, really this vertical interface, how they match together. Then we do this, years, look at the chemical information. The interesting thing over here is really the oxygen. Right across the interface, you have the oxygen deficiency. Well, can you use this kind of things to do something or not? Actually, it's very, very interesting. We found out is when you do like a conductive AFM, okay? So basically, if you look at this cross-sectional TM, you look at the plan view, the phase 1, phase 2 material, or magnify this, then we just use the conductive AFM scan across the interface. It's very, very interesting. Sorry, this colors really didn't show very, very well. Like if you look at the column or matrix, like say matrix or column, so basically it's pretty much, at this kind of given field, it's almost flat. However, when you cross the interface, right across the interface, you have a huge conductivity over there. Okay? You just really just across the interface, you form this kind of conducting channel. You think about this, actually, you can really use this more like a resistive switching device. Okay? Of course, when you try to do this, you pick up this interface. It is tough, but at least, like say we do this, you can still pattern the electrode. You can do this kind of method. Okay.
Is that usually at the interface you have oxygen deficiency?
Yes.
But typically for the oxygen deficiency, you will have become more resistive, more insulin. Is that right, or the other way?
That's a vacancy. It makes them more conductive.
In this case.
In this case. So for example, I can tell you for example, strontium tannate is transparent. You receive this single crystal, clear, transparent. You put it in a vacuum, you heat it up, and then you see the color change to yellowish. Right? If you put more oxygen, heat up even higher temperature, you can change that to black color. Okay? So basically it's just strontium titanium. You don't have oxygen at all. So make it very conductive. So that's really the way people balance the ITO, for example, transparent conductive oxide. You balance the oxygen. So you want to make it more transparent, you put more oxygen over there. That's more resistive. When you take oxygen out, you make it that dark color, more conductive. So basically that's a balance. So what kind of really application you want, you control this tool. Okay. So anyways, just to show you here, you can think about the vertical interface just really act like active devices. You can think about it that way. And also actually that's very, very interesting. You can think about the fuel cell, for example. You want high ionic conductivity, you can do all this. Okay?
Can you explain why this current as voltage curve is not symmetric? See, when you sweep, you push up to like 5 volts, and then you see the conductivity, right? So your current kind of increase from 0, let's say insulating, to say 1 nanoamp. So it depends on the section. So you can calculate or estimate the conductivity. Why not when you push to negative 5 volt?
A very good question. I believe over here, but that's due to the different, it's not symmetric electrode. You probably also have the Sharkey, like that kind of effect, the barrier effect as well, potentially. So we don't know exactly. But that's a very, very good question. So basically over here is 10 volt, it's not on. Over here is less than 5, that's on. Yeah. Since that's not symmetric, you think about this. This is, the bottom electrode is niobium doped strontium tannate. Here on the top, you have this, just like this AFM tip. Okay. That's probably potentially another reason over there. Okay.
What's the physical dimension? What's the width of the interface? What's the region?
That one, if you look at here, depends on how you look at it. You probably have to say, well, what's really the peak? Yeah, right? So, and also when you do this, this kind of measurement. That's why, I think it's so important for the field, how we can really characterize the material. It's a very, very challenge for people to do this kind of study. So I think probably I will just quickly go through, probably 10 more minutes, I'll go through this one. So talking about, like superlattices, how we do this. Here, for example, we do this like again, that's a RSMO system. Work with the bismuth fluoride, with this interface together. We study this kind of material. Like people also say, when this is ferromagnetic, this is anti-ferromagnetic. When you put these two together, do you have that kind of coupling effect or not? Okay, people actually report this like user X MCD, this technique, X-ray dichroism, that kind of measurement. This is more like a qualitatively, people see that. But the question is, can you do some kind of quantitative that kind of analysis or not? Can you really tell what's going on quantitatively across the interface? So one way we did it is we said, well, let's just put like a superlattice strata over here. Okay, so for example, here we have a 5 unicell bismuth fluoride, like a 6 unicell RSMO. Okay, we did this. The way you look at the X-ray, you look at the superlattice, even you go to 1 unicell, you still get this beautiful superlattice. You can grow this material together. Okay. The question is how you can really study this. So again, I emphasize the controlled synthesis. Make sure you do that. What we did is we use a neutron diffraction. It's measurement. So here we use a polarized neutron reflectivity. That's probably, as a physics department, is the only formula I'm putting over here in physics. So here, if you look at the index of reflection, that's also related to nuclear scattering length density or magnetic scattering length density, right? So when you do this, so basically depends on the neutron, the spin up, spin down. Actually, that's why there's a plus minus sign over here. So if that's a magnetization over there, then the plus minus, they should not equal to each other. So that's basically the physics over there, okay? So the way we did it is, since this is really thin film, the neutron mostly you apply to bulk, right? For thin film, we are talking about centimeter square, that kind of substrate. The reasons you do the reflectivity measurement, you need a large sample. Otherwise, they will not have a strong signal. So that means, so you have to have at least centimeter square. It's not a silicon technology, but you are still talking about like a centimeter square substrate. You have this quite uniform properties, right? So here you go. So here we check, for example, like a room temperature. If you look at the spin up, spin down, it's just a red and then blue. They overlap to each other. So that means there's no, across the interface, there's no magnetic property. However, if you go to, for example, like a 10 Kelvin or so, you see the difference. Oh, here, the raw data. The 10 Kelvin, you see obvious that kind of separation. So spin up, spin down, you see the difference. Probably you can ignore this, just look at over here. So this is just a magnetization as a function of the depth. Okay, see from the surface to the substrate. As you can see over here, here is the RSMO. It's a ferromagnetic. You see that kind of magnetization, it's much, much higher. However, when you go to bismuth fluoride, keep this in mind. Bismuth fluoride is anti-ferromagnetic material. But over here, actually, they go to ferromagnetic. Okay, that's more like a coupling effect. Actually, you can change here due to you put them together, you change the anti-ferromagnetic material into ferromagnetic material. Actually, we did this kind of a simulation. We said, well, that's interesting. Let's take a look at. And also another important thing that I like to remind you is here is really quantitative information. So basically, if you do this together, just look at the, like a squid, for example, measurement, you check the magnetization, they agree very, very well, exactly almost to the squid measurement result. Okay? So basically, it's really the first time we believe that's really for this material system, we quantitative just yes, they do couple to each other. Okay? And then we do the theory. We say, well, what's really going on there? Actually, here is really some calculation, user AB initial calculation. So actually, interesting thing is, if you take a look at, depends on how you terminate the interface. For example, if the RSMO is really the top, the middle layer, the interface is terminated by bismuth oxide, we believe that's based on the theory, at least, is ferromagnetic coupled. However, if you go to either lanthanum or strontium terminated, and then the anti-ferromagnetic coupling. Actually, when we did the calculation, we found, oh, that's interesting. So we know this part earlier, just show you that it is ferromagnetic coupling. We said, well, can we really, there's something can you do over here or not? Actually, interestingly, yes, you can. Here, just show you the experimental results. Say, for example, here you see this is RSMO, this is BiFeO. So basically, this is a squeeze measurement result. But over here, you see everything is negative. That's anti-ferromagnetic coupling. They don't, from that kind of like earlier I showed you. That's exactly, just match with the theory. Okay?
So which direction is your magnetization about to? Is that
Incline. Incline. Yeah. I think probably I will stop over here, give you 10 minutes or so, that kind of a question. Here, just quickly give you a summary. It's basically, I put over here, instead I say, well, everything's wonderful. I will put like the opportunities over there and also a lot of challenges over there. So probably it's, we have more questions than answers. Right? I'm hoping for is really we together, the material scientists, physicists, chemists, engineer, we work together really to solve the problem. Right? From very, very beginning to the fundamental understanding, to the device level, to the application. So I think that's very, very important. But at the same time, you can say, depends on how you do it. If you can control them, you can really do a lot of things. That's your desire. So that's just probably my summary. Thank you so very much. Okay?
So I'm trying to figure out where the chicken and the egg is. And it seems to me like you just take these materials and then put them together and then you do the theory? Or
we do both.
Okay, but so if I want to make some ferromagnetic material, can you tell me what to put together and how to do it?
That one, I hope the theory can answer that question. Theoreticians, but probably not me. But one thing, yes, actually, right now, we are doing a lot. At Los Alamos, we also have a huge effort. So we try to use a data mining or something like that. That's really user computer, just based on the published data, the first principle calculation, then we try to put the things together, predict. So hopefully you can really squeeze down. Instead, we prepare hundreds of thousands samples. Hopefully we only prepare 10, we get the answer, right? So that's, I hope I answer your question. So we are working on that, but it's totally different again. Yeah.
Can I push you a little bit harder?
Sure.
My colleagues here on this side.
So you design the material, put together, right? So
Mm.
your goal is to come up with either material with very novel property
Yes.
or better property, right?
Both.
So if
Yeah.
you only just mix them together, say, well, you know, the properties in between of these two material, that's not interesting. Or let's say, so for example, right, when you make a multi-fluid, right, you make multi-layer or pillar structures, the goal is to try to get better or say
Yes.
higher electromagnetic
Properties.
coefficient.
Yeah.
So has that been done yet? You know, say through the interface coupling that you allow you to really gain the control over the material so that you can get better or higher coupling between, say, magnetic control through the strand and to ferroelectric, say.
Yeah, simply
Can you
to
do that?
simply answer your question, yes. For the bulk, people, you know, like say for example, this ME, the magneto-electric effect, people work on the bulk. Actually, the interface things together, yes, you do already, but that's bulk. The bulk, you know, for many applications, if you go to the battle shape, like see the antenna is huge, it's like a half of the room size. But if you want to reduce the size, let's go to thin film, go to a lighter, you know, material. So in that case, that's why people are working on thin film. The thin film still a lot of challenges over there. The reasons, you know, the volume, and then how you control the interface, the many things. For the bulk, yes, to answer your question. Another thing I have to say is it really depends on your application. That's, to me, everything that's almost application-driven, specific, right? So we have to keep the application in mind. You know, at what point we stop? If you go to the industry, okay, you said, well, I have this kind of property, whatever, that's 2 order magnitude, but if they said, well, I don't want to change it, they want to make money out of this. You know, depends on how expensive. For example, like all this kind of technique we are talking about, there's a research environment. Like say we work in a lab, so we do all this kind of tricky things. But can you really make that kind of industry can scale up or not? If they cannot make money, forget about it. So again, sometimes we do this kind of incremental, improvement. Industry will take it, but sometimes even like see the dramatic, almost a quantum leap, they still don't take it.
I was told that 10 times more, that you have to be 10 times better than the conventional, say, current technology to be disruptive.
Well, another thing is really they invest a lot of money, billions dollars. You want to change their production line? Forget about it. So basically, they don't want to change it. They can buy your license your patent. They just keep it for themselves. Don't let others use it, right? And then they still keep that kind of technology. They can still make money. That's the way I deal with industry. I found out all this kind of interesting I learned.
Any other questions? If not, let's thank our speaker.
Thank you so very much. Okay.